Next participant is CP43, Cinderella TJ.
Hello, am I audible?
Yes, you are audible and your presentation is visible.
Okay, so shall I start now?
Can you please put the presentation to full screen?
Is it okay? Okay. Good afternoon, all. My name is Cinderella TJ. The title of my research, paper is Connectedness of the Space of Homomorphisms of a Compact Manifold. Now let's move to the introduction. For a metric space XT, let C of X be the set of all continuous functions on X. We know that it is a group under the operation composition of functions. The two commonly used topologies in the space of functions are the uniform topology and the compact open topology, where the uniform topology is generated by the supremum metric row that is defined as rho of fg equal to supremum over all x in x, d of f of x and g of x. And the compact open topology is the topology having its subbasis as set of all k u's, where k stands for a compact set and u stands for an open set. And set k u is defined as set of all continuous functions that takes the image of k into u. Consider this set h of x, which is the set of all homeomorphisms. We know that a function is a homeomorphism if it is 1, 1 onto continuous as well as its inverse is continuous. This set h of x is not just a subset, but it is a subgroup as well as a subspace of C of x. We call the space h of x as the space of homeomorphisms. When x is compact, the above two topologies coincides. Now, this is what my paper is all about. That is, if X is a compact manifold, we have the result that says that a compact manifold of dimension greater than 1 is n-homogeneous. Using this, we define the sets H of xy and bracket x. And finally, we prove that the space of homeomorphisms is disconnected. The terms used in this slide, we'll see to it in the coming slides. Now, moving to the definitions that are required. First definition is topological group. As the name says, the topological group is a group that is also a topological space satisfying two conditions. First condition is that the map from G cross G into G that sends a general element X cross Y into X dot Y is continuous. Here dot is the dot that is used as the dot operation in G. And the map from G into G, which sends an element to its inverse, is also continuous. As an example, we have Cantor set. Now, coming to the second definition, that is topologically complete. We say that a topological space is topologically complete if there exists a metric that generates that topology and a space together with that metric is a complete metric space. As an example, we have set of irrationals. Now coming to the next definition, that is homogeneity. A topological space X is homogeneous if given any 2 points, there exists a homeomorphism mapping one to the other. And also we have a result that says that every topological group is homogeneous. And also we saw what is a topological group, and we already saw Cantor set as an example. So now we can say that Cantor set is homogeneous. Next, coming to the other definition, that is n-homogeneity. We say that a topological space is n-homogeneous if given two sets of n points, say x1, x2, etc., xn, and y1, y2, etc., yn, there is a homeomorphism that maps the corresponding elements. That is, there exists a homeomorphism that maps xi to yi. Now, moving to the last definition, that is manifolds. Or in general, M manifold. We say that an M manifold is a Hausdorff space with a countable basis such that each point has a neighborhood that is homeomorphic to an open subset of Rm. A one manifold is often called a curve and a two manifold is often called a surface. As examples, we have finite sets and Cantor sets are zero manifolds, intervals and circles are one manifolds, surface of a sphere, torus are two manifolds. Now, coming to the main part of our paper, that is about the results. First result says that if X is a compact compact manifold and F is a continuous function, and if X and Y are two periodic points of the same period n, then there exists a homeomorphism mapping the orbit of one to the orbit of other. Here orbit of X is denoted by O f of X, which is defined as set X, comma f of X, comma etc. Fn minus 1 of X. That is, this theorem guarantees that there always exists a homeomorphism mapping the orbit of one to the orbit of other. We consider all such homeomorphisms and we denote it as H of xy. Now, for a fixed x belonging to per n of f, which is the set of all n periodic points, we define set bracket x as the set of all such H of xy's, where y is allowed to vary in the set per n of f. And it is easy to prove the below given properties as A, B, and C. Now moving to result 2, which says about H of xy, and it is a closed subset of H of x. Now result 3, for a fixed n, what if the set per n of f, that is the set of n periodic points, is dense in x? Then the set, corresponding set which we can think of that can be dense in H of x is the set given as union H of xy. And we found that it is not dense in H of x, but it is a closed subset of H of x. And in result 4, which it is an extension of result 3, instead of making an n fixed, we allow n to vary between 1 and infinity. And so instead of per n of f, we'll have per f, that is set of all periodic points. What if the set of all periodic points is dense in X? Then the corresponding set is the double union set, and we again found that it is not dense in H of X. Now moving to result 5, which says about the set bracket X, and it is found that bracket X is a closed subset of H of X such that the intersection is non-empty. Now moving to result 6, which says that if X is a connected topological space, then X is the only set that is fixed by all the homeomorphisms. Now, before moving to our main result, let's see some properties of the space H of M. That is, if X is a that is, if M is a compact manifold and H of M denotes the space of all homeomorphisms on M, we have these results. That is, it is a separable metric space, it is a topological group, as well as it is homogeneous, and it is topologically complete. And finally, now we have proved that this space is disconnected. That is, for a compact manifold, its space of homeomorphisms is disconnected. Whereas if our space is not compact, we already have in the literature that the set epsilon of H, which is defined as given, becomes a proper Klopen subset. That is, when our space is not compact, this becomes a separation, so that we can say that its space of homeomorphisms is not connected. And and finally, coming to an observation, which says that if A is a set that is dense in X, then can we say that the set HA of X, where HA of X is defined as set of all homeomorphisms, that when restricted to A is again a homeomorphism. Can we say that the set HA of X is dense in H of X? And we again found that it is not dense in H of X with respect to these three topologies. That is compact open topology, product topology, and uniform topology. And that is all about my results. And these are my references. Thank you.
Thank you. Any queries? Do you have a question here?
Last result. Last result. Go to the last result. Show your last result.
Ma'am, I can't hear. Last?
Show your last result.
1 second.
You have a question here.
Which result? This one. Before this observation.
Yes. Yeah, this one. In this observation, we have h of x, that h of x is constitute three different topologies, which is compact open topology, product topology,
Yes.
and last one is
Uh,
uniform topology. What about
okay.
box topology?
Uh, Box topology also, I think it is true. That is, even with respect to box topology also, this set won't be dense in H of X. I think I have a counterexample for that.
Okay. When you want to say the compact open topology, is this true for the finite complement topology? Because you take
Finite,
homeomorphism.
which topology?
Complement, finite complement topology, or infinite
That is
complement topology.
finite
Talk about the homeomorphism. Your first case is compact open topology.
I didn't get the question.
In this observation, did you
Okay.
observe this HA of X constitute
Mm.
infinite complement topology or finite complement topology? Did you observe it or not?
I haven't checked for that.
Yeah, okay, because
Actually, in H
compact
of
open
X,
topology, and then
these are the
you say
common
one
topologies
thing,
which we use.
box, that is box X
Mm.
nodes, that is not box X. In your one of the result, you mentioned
Okay.
box X. That is not a box X. It is a whole integer part of X. The
Okay.
information is not clear, but your results are awesome. Thank you.
Okay. I don't know whether I could clear her doubt.
Guys, clear.
Yes, it is clear.
Okay.
Okay, thank you. Next presentation is CP44 by Ms. Rajagiri. Sriya?
Hello.
Yes.
Can this is it clear to
Yes, your
is it
presentation
visible?
is visible.
Okay.
Can you put it on slideshow?
Yes. Okay. Good afternoon. I am Ms. Rajagiri from Rajagiri School of Engineering and Technology. This is a study on Ramanujan graphs. A study of Ramanujan graphs gives ideas from different various branches of mathematics like number theory, group theory, representation theory, etc. Now, starting from the expanded graphs, a boundary of A is the set of all edges between A and B minus A. The Cheever constant h of G is defined as the minimum overall cardinality of boundary of A by cardinality of A. Then expanded graph is the k-regular graph G with n vertices if h of G is greater than or equal to C, which is a constant. Now, moving to an expanded family of graphs, which is a family of k-regular graphs, which has Cheever constant greater than or equal to C for all the graphs in that family. Now, expanded graphs are regular graphs. So we can see the spectrum of the regular graphs. Then K is an eigenvalue of a K regular graph. We can arrange the eigenvalues of that graph as K equal to lambda naught greater than or equal to lambda 1, etc. Lambda n minus 1. Spectrum of bipartite graph is symmetric about origin. That is for bipartite graph, bipartite K regular graph, it is between minus K and K. For all the eigenvalues, always less than or equal to delta of K, which is the maximum degree of the graph. K equal to lambda is an eigenvalue with multiplicity equal to the number of connected components of G. Now, there are some properties of expanded graphs. They are highly connected. They are, it has less diameter. Then Chung's inequality shows that the diameter is always related to the second largest eigenvalue. That is these results, we can see that the smaller the second largest eigenvalue, smaller diameter and higher the connectivity. This is an inequality which connects the next is an inequality which connects the Cheeger constant and the second largest eigenvalue, that is G minus lambda 1 by 2 less than or equal to H of G, where D is the degree of, that is the regularity of the graph. These are some examples of expander graphs. They are complete graphs are expander graphs which has the Cheeger constant approximately equal to n by 2. Okay, cyclic graphs are Raman expanded graphs which has the Cheeger constant converges to 0 as the value of the n increases. That is, higher the value of the n, the Cheeger constant decreases. That is, reduces to 0. Now, moving to expanded graphs, which is a finite connected k-regular graph, which has all its non-trivial eigenvalues less than or equal to 2 into root k minus 1. We have already seen an inequality h of x greater than or equal to k minus lambda 1 of x by 2. From this result, it is clear that the Ramanujan graphs are good expanders. Allen-Bopina theorem, which describes about how the infinite family of regular graphs how the spectrum of the regular graphs goes as n tends to infinity. You can see clear that the limit infimum of such graphs is always greater than or equal to 2 into root k minus 1. Peterson graph is an example of of a Ramanujan graph which has the second largest eigenvalue equal to 1. Now to construct Ramanujan graph, we need regular graphs. The most easy way to construct regular graphs is by means of Cayley graphs. That is, we need a group gamma and a symmetric subset of gamma. Then the Cayley graph is constructed as V of G, that is vertex set which has gamma as the entries, and E of G equal to set of all GH such that G inverse element of S. Cayley graphs are always cardinality of S regular graphs, and G of gamma S is connected if and only if S is a set of generators. And to know about the spectrum of the Cayley graphs, we could find help from this theorem. That is, if gamma be the finite group and this is symmetric subset of gamma of size k, then the eigenvalues of that distinct matrix G of gamma S are given by lambda x equal to 1 by lambda chi equal to 1 by chi of S, sigma S element of S chi of S, as chi ranges over all the reducible characters of gamma. And we can see this is a particular result by Murthy and Friedman, which says the abelian Cayley graphs are rarely Ramanujan. So, in order to find regular Ramanujan graphs, in order to find Cayley graphs which are Ramanujan, we have to consider non-abelian Cayley graphs. So, Paley graphs is an example of Cayley graph, which is Ramanujan, which is 1 by 2 into q minus 1 regular, where q is the power of prime, is congruent to 1 mod 4. This is constructed in this way. Here, the group we take is fq star, which is equal to fq minus z0, which is the finite field of q elements. And symmetric set we consider is fq star square, which is the set of all r element of fq star, and x square equal to r for some x element of fq star. And by this way, we can construct a Cayley graph for any q, which is a power of prime. And it is clear that the Paley graphs are strongly regular graphs. Its parameters is RG of q into 1 by 2, q minus 1, 1 by 4, q minus 5, and 1 by 4, q minus 1. And since it is a strongly regular graph, there are 3 distinct eigenvalues, which are 1 by 2 into q minus 1 and plus 1 by 2 into minus 1 plus or minus root q. The second largest eigenvalue, lambda 1, is equal to 1 by 2 into minus 1 plus root q, and then which is clearly less than the Ramanujan bound. So it is clear that it is a Ramanujan graph. Now, one of the explicit constructions, this is a famous construction, is the Lebowski-Phillips-Serner construction. We use the group here as PGL, PG, projective general linear group of 2Q. We take 2 primes P and Q, which is congruent to 1 mod 4. Then find integer solutions. There are P plus 1 integer solutions for the equation A square plus B square plus C square plus D square equal to P, where A greater than 0 and is odd, and the other integers are even. Then we can one-to-one correspondence between a U element of the A element of Z and this matrix, the A plus UD and C plus UD minus C plus UD, A minus UD, then which will become a symmetric set of PGL2 of Q. Then we can find the Cayley graph from here when Q greater than 2 root P. Then it was proved to be Ramanujan. So we get the infinite family of Ramanujan graphs for powers of P, which is P plus 1 regular. Now, considering similar examples of graphs, we take prism graphs. That is, the first figure is the prism graph of 3, that is PG of 3, PG of 4, etc. Then we can find that it is Ramanujan when n is less than or equal to 50. Now, to construct an infinite family of bipartite Ramanujan graph, infinite family of bipartite Ramanujan graph is possible by the method of 2 lifts. Here we take a particular graph G and make 2 copies of the graph G, then delete same edges from each copy, then cross those edges. This is a particular 2 lift of the graph. Then we construct the adjacency matrix of the graph GA and find AS. That is, we replace 1 with -1 in each case when a particular crossing is given. Then we find A and AS. Next, we find A1 and A2 by this equations. Then we can find that A dash, which is the adjacency matrix of G dash, equal to this form. And also these are connected by these equations. Hence, we can find that the eigenvalues of G dash are the union of eigenvalues of A and the eigenvalues of AS. So, if we could find a particular lift which does not exceed the eigenvalues by the Ramanujan, that is, which does not increase the eigenvalues less than Ramanujan bound, then we can say that that particular graph G dash, which is formed, is Ramanujan. By Bilu and linear construction, it was proved that such 2 lifts exist. Thus, the graph formed from G is, since it is bipartite, we could get an infinite family of bipartite Ramanujan graph all degrees at least 3. These are the references. There are also other infinite families of Ramanujan graphs. These are the references. Thank you.
Thank you. Any queries? Thank you, Ms. Ria.
Thank you.
Contributory paper presentation session 8 is over. Thank you all participants. Request you to join the main Zoom meeting link. Thank you.